The book Orthogonal Functions, Moment Theory, and Continued Fractions, Theory and Applications, edited by William B. Jones and A. Sriranga, offers a comprehensive exploration of advanced mathematical concepts that have profound implications in both theoretical and practical domains. This volume compiles the proceedings of a significant conference held in Campinas, Brazil, bringing together experts to discuss orthogonal functions, moment theory, continued fractions, Gaussian quadrature, Stieltjes transforms, linear functionals, and Pade approximants. These topics have historical ties to the analytic theory of continued fractions that emerged in the 19th and early 20th centuries. The book aims to bridge gaps in understanding by showcasing how these subjects intersect and contribute to broader mathematical applications. The conference's primary focus was on the analytical dimensions of these subjects, but it also explored practical applications in fields such as special functions, frequency analysis, digital signal processing, and related computational methods. This dual emphasis is reflected throughout the volume's content. The sessions included not only reports on recent research findings, but also collaborative efforts that resulted in new discoveries during the event. These collaborative problem-solving discussions aimed to identify future research directions within these fields. The conference was organized by A. Sriranga, Eliana XL de Andrade, from Brazil, and William B. Jones from the University of Colorado at Boulder. This collaboration benefited from various funding sources, including grants from Brazilian national scientific councils and universities across different countries, facilitating a diverse gathering of scholars who contributed significantly to the discussions and outcomes of the workshop. The first part of the book delves into the comprehensive examination of Chebyshev polynomials, focusing on their properties and applications. The study by Todik establishes that the problems concerning the Chebyshev space, HH, can be transformed into equivalent problems involving algebraic polynomials of degree not exceeding n. A significant finding is a simplified proof of a Jackson-type theorem provided in one section, which links to Lagrange interpolation challenges using SGM, polynomials at zeros of particular functions. The paper also explores the extremal problem solutions within the context of LLP spaces. The text details basic properties of Chebyshev, SEN, polynomials, and their connections to classical theories, emphasizing both theoretical foundations and modern advancements in mathematical analysis. It introduces a transformation between variables represented as EX, UX, UX, revealing a one-to-one mapping across intervals that facilitates deeper analysis. The discussion also covers representations involving cosine functions and recurrence relations for Chebyshev polynomials. In conclusion, this part of the book provides insights into polynomial behavior within specific intervals, highlighting both classical theories and modern advancements in mathematical analysis. The second section discusses advanced mathematical concepts related to the Stieltjes moment problem, SMP, and its extensions, particularly focusing on indeterminate strong Stieltjes moment problems, SMP. The text begins by introducing the SNP as a framework for analyzing sequences of real numbers. It establishes that a solution exists if a bounded, non-decreasing distribution function can be constructed with infinitely many points of increase. The authors delve into specific inequalities necessary for solving the SNP, emphasizing their sufficiency in ensuring a solution's existence. A significant theorem connects the solvability of the SNP with conditions derived from positive definiteness of quadratic forms. The narrative transitions to formal power series and their role in constructing solutions to indeterminate moment problems via polynomial fractions, PC fraction. This approach enables the establishment of unique sequences associated with both modified PC fractions and their canonical contractions. The text also explores main results regarding natural solutions to SMP characterized by specific orthogonal Laurent polynomial sequences, OLPs. It posits that there exist natural sequences whose properties are preserved under transformations related to these moment problems. The authors argue that such relationships not only provide insight into existing solutions, but also contribute to establishing new methodologies for approaching indeterminate moment problems through uniform convergence criteria on compact subsets. The third part focuses on the properties of symmetric orthogonal polynomials, particularly in relation to a specific transformation denoted as A. This transformation applies to polynomials identified as A, B, which are linked to the concept of orthogonal Laurent polynomials. The article extends this framework into the complex domains known as ZOT, and W. The text details how certain conditions imposed on continued fractions create a more controlled environment for analysis, allowing for stronger assertions about properties. It highlights significant results regarding moment problems with discrete distributions, emphasizing that under these assumptions, not only do zeros exhibit simple characteristics, but also maintain a necessary order which separates them clearly. Within the complex plane, the fourth section discusses advanced mathematical concepts related to continued fractions, focusing on extended multipoint PADE approximants, NP fractions. The text presents various polynomial forms utilized for the canonical numerators and denominators of these fractions. It emphasizes that the modified PC fraction leads to formal power series that can be approximated using two-point PADE approximants. The paper introduces orthogonal Laurent polynomials as canonical denominators derived from a specific orthogonalization process, highlighting how they relate to polynomial sequences connected to various solutions of SMPS. The authors introduce notation for moments and demonstrate how various results hold under specified conditions for these weight functions. The final section delves into advancements in rational approximation and interpolation, particularly focusing on Neven-Linna functions. It discusses a measure, U defined on the real line, and its associated Neven-Linna transform, emphasizing that these transforms yield holomorphic functions in the upper half plane with non-negative real parts. The document also explores moment problems, particularly the hamburger moment problem and its generalizations. It proposes conditions for existence and uniqueness of measures through the analysis of generalized moments derived from polynomial bases. This leads to discussions on cyclic and non-cyclic cases, addressing how variations in sequences affect underlying moment problems. In conclusion, this edited volume serves as a comprehensive resource that reflects contemporary research trends concerning orthogonal functions and their applications in moment theory and continued fractions. It aims to make complex mathematical theories accessible not only to mathematicians, but also to scientists and engineers interested in applying these concepts practically across various domains. Through detailed presentations of ongoing research projects and collaborative problem-solving efforts during the conference, it fosters an environment conducive to advancing knowledge within these interconnected areas of mathematics. By bridging gaps in understanding between theoretical foundations and practical applications, this book not only enhances our comprehension of advanced mathematical theories, but also provides valuable tools for solving real-world problems. The interdisciplinary nature of the topics covered underscores the importance of this work in driving innovation across multiple scientific fields.